So there is basically, if you look at basic design of multi-threaded systems, let's look at first the event loop, right? So you have the event loop, which basically looks like this. So let's put this loop here. You get some data or some event, you do one computation one, and then you have some sort of blocking, and then you do the next section of computation. And then when you have finished, let's say here you have only 2 sections of computation. Apologies for the handwriting. My pen is not working very well. I hope you can read. So you do some computation with when the event arrives. You block for some reason. It could be because this blocking is because you are sharing either data or state. So state meaning you're waiting for some other thing to arrive. For example, data to be arriving in a hardware interface, or you may be sharing data with another event loop itself. So this blocking basically, so when you look at the performance here, the total execution time plus the waiting time that decides the response time of the overall cycle. So if you linearly add these, so let's say T1, this is T delay, and then T2, your total response time is a summation of all this, right? So this is how you are basically reducing the performance. So basically because of this blocking, so if you remove the blocking, T1 plus T2 is the minimum required computation to make a response. So how do you actually achieve that? So where is the delay coming from? If you think carefully,
Dozed off.
I'm sorry, somebody said something. Am I audible?
Sorry, it was me. I was talking with myself.
Oh, okay, sorry. So yeah, just wondering if I did something. Okay, so we're talking about designing with an alternative, which basically is called shared nothing model, right? Shared nothing model basically means, let's say you have several threads of communication. Each is an event loop. They obviously wait for an event and then do their computation and then go back to sleep. And the same thing here. So there is nothing that is shared between, say, let's say thread 1 and thread 2. There is nothing shared. So nothing shared. Maybe there is a synchronization, maybe not. So then you are basically having true concurrency if they are running on 2 different processors. And you may have pseudo concurrency if you are multiplexing the same processor. So basically that is where the thread scheduling comes into picture. So it may have priorities and so on and so forth. So when this is waiting, this could make progress if it has data. And so they basically do the context switching. So this context switching is required in if you share the CPU, okay? But these 2 threads are independent mostly, because of which there is, while they may interleave their execution, they are preempted and so on. They are not actually wasting time waiting for any shared data to be available to them. Now, how do you do that? Basically, that is where the event-driven programming model comes. So think of each event is feeding a computation. Okay? The computation can be anything. So you wait for event. Event is basically something coming from the I/O interface or anything, any signals that you may get, so that you can make, and then do your computation, and then repeat. This is what I showed earlier, right? Now, how can you avoid sharing data? That means all data is private. So you need data, all data is private. So what it means is that the event that you are getting, it could be a message that itself has all the necessary input data, right? In order to make the computation. That means it is not stored elsewhere and shared with another. It could be stored in, so it is coming in the input event itself. So in the, if you see in this wait for event, the event will have the parameters. That parameters is what the computation is executing. Of course, there may be much more than the parameter, because the event size may be limited. So you may have more share, more buffer data. So let's say you have a packet of a packet is arriving. So the event signals the packet arrival. And of course, it may give some parameters like what kind of packet it is. But the actual payload may be in some global memory. The thing is, while from a C programming point of view, it is a global buffer, it is still private to this thread. In the sense, no other thread is accessing either for reading or writing. So this global memory is global in the sense of C storage concept, but it is private for the thread. So there is nobody else accessing that. So it is not shared data. So for example, you have the ISR, it allocates buffer, or it just writes to pre-allocated buffer and then sends the pointer to the buffer as a parameter of the event. So the thread that processes it accesses the event queue. So it gets unblocked, right? So it accesses the event and then extracts the pointer and then accesses global data or global buffer. Now, all these are non-blocking. Basically, it can do happily without worrying about other threads. Then the only thing that interleaves the threads is that if some other thread similarly gets some data event and then it wants to execute, it is basically the relative priority of, so the interleaving is not avoidable by preemptive priority scheduling. Now, you can also do in an alternate way, which is basically what is called run to completion model. This is an alternative to preemptive priority. What it means is that we talked about waiting for an event and then compute and then go back to wait. Now think of this compute. We don't know how long it will take to compute. It may be small computation, it may be large computation. And then similarly, another thread B is doing the same thing. It is waiting and then it is doing its computation. And then you repeat. The problem is when this is higher priority, you are stopping it here, doing some computation here. And when it finishes, you are continuing from where, so it comes here, you are continuing from where it stopped. Now, you could avoid that because there is a, so what is the problem there? You have the context switch overhead. So one could avoid in the event-driven programming by switching to run to completion. How do you do that? Now, we talked about the event queue. So basically it is nothing but basically it's a message form. So where is the event coming from? Mostly from a hardware driver, maybe it could be an ISR, or it could be another producer thread. Now that's normal to expect. So you do the computation. Now it is also possible that you break your computation into stages. Stage 1 computation, stage 2 computation, and so on. Stage K. Now this is expected to be the most critical minimal computation that you need to do before you can go to stage 2. So you, given the application logic, you will be able to decide what needs to be done. For example, copying some data from a hardware buffer or anything that is temporal. So you do the critical processing first. Then you have now cached all the private information, private data required for completing the overall computation. So you can actually say, I will do it when when the processor has time. So I will post an event back to myself. I have finished. So here you put a message saying that stage one done. It's a signal. Then what happens? The same if so there is only one place you are waiting. When the cycle happens, this message is picked up. It can proceed to stage 2. Here you will say stage 2 come done. And then when stage n is completed, you are completed the entire operation. What happens is that this is the point at which you are waiting, and you are pacing yourself by organizing your computation into smaller segments. In between, you are allowing other threads a chance to run. So remember, when you are having pseudo multitasking, which is basically multitasking is basically pseudo concurrency. You are giving CPU, you are sharing CPU by blocking one thread and giving to another thread. So the blocking point is basically the event queue. So at that point, basically you could do a scheduling. So basically it means you are normally in run to completion. It's also called cooperative multitasking or cooperative scheduling. So there is no context switch required. So you are yielding the CPU. So many threads, application level threads, which run in a single process, you can use cooperative scheduling using what is called yield CPU one function call. Basically, instead of waiting, you are basically saying, I now yield the CPU to whoever is ready to run, whichever thread is ready to run. So the idea is that there is no context switch. Because you have done one stage of computation, you can continue cleanly. So what is context? What is context? Basically, it starts with the program counter, maybe the CPU registers. And if you're having thread related housekeeping information, like what is called the task control block in an operating system, right? Or in the process context, it is the process control block. So basically, this is the context that if you have opened certain files, it will be part of the process context. Excuse me. If you are holding some resources, all those are basically context. So by doing cooperative scheduling, all this is not required, because yes, you need to continue the next computation, but so you are not saving the CPU, the program counter or CPU registers. Why? Because when you get a chance to run, it will always start at a known place, start in the event queue. And then you will have a switch statement on the event type, and then you will say, okay, case stage 2, stage 1 computation, then call a function which is stage 1 handler, and so on. So basically, you don't need to store the program count. It is stored, no doubt, when you are yielding the CPU, but it is not necessary to save any registers, etc. It is basically when this thread is yielding the CPU to other, it knows exactly where to start from. You know, there is only, so as opposed to preemptive scheduling. So preemptive scheduling, you have a lot of computation. You may be preempted at any point in time by it's basically asynchronous. So the return address is not determined. So the return address is a context, that is the program counter value. So it is undetermined. So you need to save it. Whereas in a non-preemptive run to completion, you are always yielding. You're not preempted. You're yielding at a specific point in code, which is known. So you don't have to save the program counter in this sense. Of course, the processor needs a program counter, which is for the new thread, but it is not part of your thread context. So you don't have to save registers, you don't have to save anything other than you just have to wait for your turn when another thread is yielding the CPU. So it is very efficient that way. So to summarize, we are talking about shared nothing model, which is an extreme, but you may have some, or shared little. What is shared little? You may be forced that thread A and thread B have to share some information, some state. Keep it minimum. It may be a state variable, but keep it minimum, because then you have to make a mutex for this, and mutex may mean blocking, or you may do a lock for this, which may be spinning, which is fine. Or they are occasionally synchronizing, and this information it's not like held forever. It is just when you're up. So this may be updating the state, this may be reading the state, or vice versa. So it's a very small known operation. So that is why it's called shared little model. Shared nothing model is an extreme where absolutely there is nothing that is shared except the CPU, and that CPU sharing is also via run to completion model and not non-preemptive. So this is how you will do. So event-driven programming typically is done by many things. One is avoid sharing, keep data and state private to the thread, and the whole information is available in the event, and then you are breaking the thread execution in a very known place where therefore there is no context to be saved. Okay, so Shankar, does it satisfy you? I see 3 questions. Okay, so I'm sorry, I'm seeing this question. What is the question for this event loop topic? So basically, in the event-driven paradigm, how do they overcome the bottlenecks of systems with shared concurrency? So I hope that makes sense to you now. Mohammed is saying thread global variables are in thread stack and therefore private to the thread itself. Yes and no. You could say that what is thread stack? You could say it could be thread local variable, or it could be a pointer to a global variable. Now, thread stack is also limited shared resource because you have to configure for each thread a stack size per thread. Now, how do you size that? And then your overall stack usage is a sigma of all the threads and their thread stack size. So you don't know how much to configure for each thread. So you may want to configure as little as possible so that your total stack usage is not wasted. And therefore, even though, yes, you're right, the thread context is private. It could be in the stack, or it could be a global variable in memory in the C sense, right? But not, in either case, not shared. That is the most important.